So let's continue. Today, this is lecture 17. We're going to be talking about simulation. I'm going to start pulling the rug out from under you, okay? So before we knew the value of n, and then we can simulate and do some stuff on that based on the value of n. Let's recap really quickly what we did. Our assumptions were that the planes are numbered 1 through n. We don't know n, and we want to figure out n. Okay? And the assumption that we made was that the serial numbers of the planes are uniformly drawn at random from 1 through n. Okay? So let's talk about, oops, oh, that's slipping. All right. Move that over, full screen. Excellent. So I have here a notebook, and I have here a mysterious value of n. So here, let's say n is 300 again. And I took some observations, and I look at my observations. Okay, so if n is 300, my observation should go between 0 and 300. But if you look at that, it's not. Talk with your neighbor about what you think the actual value of n might be. So if n was actually 300, I would not be able to observe this, right? What do you think the actual value of n is? I'll give you some hints. Here is observation.max. Here is observation mp.average observation. Okay. All right, go talk.
I think now that I think like 500, yeah, that's 520 or something. Between 500 and 600.
All right, let me hear some guesses. What do you guys think? Just yell out some numbers. What do you think? 1,010. Alien says 1,010. Anyone else? Just give me two more numbers. Yeah, Amanda. Huh? 1,100. Anyone else? One more number. I just need one more. 1,100. Andy.
1,030.
1,030. All right. So you guys are pretty close. So the actual number was the number of Z's in all of Shakespeare's plays. So the number of Z's in all of Shakespeare's, I don't know how to spell Shakespeare's plays, and that was actually 1020. Okay, so that's how we figured it out. But let's suppose I didn't know that. So how would I figure it out? What is n question mark? Okay, so I run this, and I see, okay, I get these estimates, run that, and I say, okay, it looks like my max estimator got around 1,000, probably stops right here at 1020. And then my 2 times average is kind of flatter and more spread out, but it's centered at 1020. Okay, so the actual number of n was here. So just to recap what we did from an hour ago, not yesterday. And what I want you to notice here is oh goodness, okay. I ended discussion just now talking about looking at the shapes of these distributions, right? Shapes of these distributions. Max is kind of like squished together, taller. 2 times average is kind of spread out, right? And these kind of come back to some core ideas of estimation called bias and variance, right? So bias is basically, on average, will my estimation be correct? Okay. So a biased estimate, such as my max estimator, says on average across all my samples, I'm going to get something that's a little bit less or a little bit more than my actual value of n, right? So the max, when I took the max, I'm actually going to, on average, get a little bit less than my value of n. So that's called a biased estimator. It's a little bit biased. It's a systematic error in one direction. Okay, so good estimates typically have low bias or no bias. That's one criteria. On the other hand, we have variability. So it's not exactly variance, which is like a specific stats quantity. Variability is, in this case, I'm just referring to like how spread out my estimation is. Okay, so the degree to which the value of my estimation varies from one sample to the other. Because if I have high variability, it makes it a little bit harder to estimate, right? Because my 2 times average was more spread out, I'm less certain that the 2 times average estimator will give me a good value of n, because I could get something farther away or could get something above. So good estimates typically have low variability. Unfortunately, typically when you have something that has low bias, chances are more likely that it has high variance. And when you have something that has low variance, it has more bias. So for example, in the case of our max and our 2 times average, our max has bias but has low variability. My 2 times average is unbiased, but it has pretty high variability. So you're supposed to discuss it, but I gave it away. But basically, there's a trade-off, right? Life is tough. There ain't no free lunch. Is there a way to get an estimator with a low bias and low variability in this case? So I'm taking a look here. I did the 2 times average, did the max. Is there some clever way to get an estimator with low variance and low bias? Why don't you think about that? Talk it over with your neighbor for a minute.
How are we supposed to know that? Well, maximum has low variability because we have a maximum already. It cannot get any higher than that, right? 2 times average, or yeah, well, there's a higher limit, lower limit, I guess. Yeah. Because it can get higher than that maximum, where we're multiplying the average by 2. So whatever the highest possible could be accurate.
All right, what do you guys think? Can I figure out a more clever estimator? Ilian, what do you think?
Is there a way to use the 2 times average technique to take a range that's closest to the average? So like you take only values that are, I don't know, 0.3 off from the average?
Yeah, so Ilian says, can I just take my 2 times average and kind of slice off the ends here? Perhaps, although it's kind of hard to do that because this is kind of showing me like the average of all possible estimations, right? But in reality, I only have one sample. If I only have one set of planes and I look at that set of planes, I won't get to do like more of these guys. I can only do like 2 times the average of that set of planes, and that's it. So good idea. Maybe there's a way of coming up with an estimator that is narrower, but we have to figure out what the estimator is. So given my one sample, what can I compute that will give me something with low bias and low variance? Any other ideas? It's kind of tricky. Yeah, Luke?
How about 2 times median?
How about 2 times the median? Well, we could try it out. So take this. Let's try out a more clever estimator. Ah, OK. Looks like I already have it here. I don't want to spoil the surprise. OK, goodbye. All right, so let's try 2 times the median. Double median. All I really need to do is make another array here. So let me do that. Equals make array. Let's do np.median. Is there a median? np.median. Ah, convenient. So double median. I'm just going to take that and do double median. Okay, that's it. Keep track of everything plus 2 times the median. Let's see what happens. 2 times np.median observation. That double median. And let's see what happens. Okay, so I have here max 2 times the average and 2 times the median. Let us see what that gives us. Estimates.hist. I'm so excited. What could it possibly look like? And oh, unfortunately not. It's a little bit more spread out than it was before. Well, we tried. OK, any other ideas? OK, so I have an idea. Conveniently enough, it's the right idea. What a coincidence. But what I can do here is notice that the max estimator is just a little bit off, right? So it has low variance, but it's a little bit biased towards negative, towards 0, right? a little bit biased. What if I could just shift it up by a little bit? Okay, so let's try to take the max and shift it up by a little bit. And what I'm going to do there is take the max and say, OK, let's do max plus my min. Okay, so max plus my min. So instead of taking just the max of my sample, I'll take the maximum and the minimum and add them together. Okay, so my intuition behind that is saying, OK, if my planes were numbered 0 through 100, chances, and I take a sample of 3, right? So I take 3 planes out of 0 through 100. Chances are, roughly speaking, that I'll get a plane at like 25, a plane at 50, and a plane at 75. So if I take the max, which is 75, and the min, which is 25, and add them together, I should get back 100. That's kind of my intuition behind it. So let's try that. Max plus min, make array. Max plus min. Max plus min. Let's take my observation and do np dot max observation plus np dot min. Sorry, it's going off my screen. Observation. Okay, just move that here. Okay, so max plus min, max plus min. Let's take a look at what that gives me. So I have here max 3 times the average and max plus min. Let's try to histogram those and see what we get. Okay, so indeed, we see the max. So here's my yellow as a max. 2 times the average is this dark blue. And max plus min is this light blue guy right here. And in fact, it is centered at 1020. And in fact, it is narrower than 2 times the average. So it looks like it is a better estimator than these two. Okay. So there's a way we can see, there's a way we can measure variability, right? So it looks like this max here is like pretty close together. The min here, max plus min is pretty close. 2 times average, not so close. There's a way we can measure that. And the way we can measure that is saying, OK, on average, how far away are my observations, or my estimates from the average estimate, right? So I take my middle value. So let's take a look at my max. Just the yellow. Let me scroll up. Maybe it's a little more clear. OK, so here we go. Here's just the max. The middle value, the mean of my max of these estimates is probably right here, maybe like 980. I can look at how many values were far, like how far away these values are on average from that. So I can take the estimations. So I have my estimates. I can take estimates.column 0, take my maxes. And I can do, let's say, take the mean of these maxes. So here's my average max. I can just take estimates.column 0 minus that to figure out, OK, on average, like these guys were this far away from my mean. Here's an array of differences from my mean, and I can do absolute value. It's not super important to know now. I'm just showing you in advance. So here's my absolute value, and then I can take the mean of that. So this is like super complicated. I'm kind of like going ahead of myself here. But let's just show you that there is a numerical. I'm just trying to show you that there is a numerical way to measure variability. And basically, the idea is the more variability that I have, the bigger that number should be. Okay, so just giving you kind of like a preview of what's happening. So mean. It looks like my variability here is around 22. I can just repeat that for different columns. 1, 1, 2, 2. You can see that my max estimator has a very low variability. My 2 times average has a high. And the max plus min has a little bit higher than my max, but it is less biased. OK, yeah, Elliot?
So just a question about your max plus min estimator.
Yeah.
Are you adding the minimum value or the difference between the minimum and maximum value?
I'm adding the minimum value. So if I have 25, 50, 75 as my planes, I'm taking the min, which is 25, taking the max, which is 75, adding them together to get 100. Okay. So now your brains are probably going like, well, is there a better estimator? Maybe there is. Maybe you can find out. But you can try it out. All you have to do is copy and paste my code, write an estimator here, and see what you get. Okay, so try it out. Maybe you'll find something better. Let's talk now. Or let's take attendance now. OK, great. OK, resume. Go ahead. watch my number go up. How fun. Okay. Yeah. Oh, whoops, here it is. bit.ly/@-d8. Okay, that's the URL. All right. So we spent some time trying to figure out whether we can take a sample and use that sample to estimate some number about the population, right? So I took my sample of planes and tried to estimate how many total planes are there. The other way I can use a sample is to say, take my sample, take a look at what I think the population is, and say, did my sample look like it came from my population or not? Okay. So in a real sense, this is an example that we like to use is when we talk about jury panels, right? So in specific, the way jury panels are selected is there's a bunch of eligible jurors in a county. So basically everyone in a county over the age of 18 and registered to vote. There's some criteria, more criteria there. Okay, there's some eligible jurors, and we get to the jury. But in the middle, there is a list of eligible residents. So we select out some of the eligible jurors. And then from the eligible residents, we select out a jury panel. And then from the jury panel, we select out a jury as a final people that make the decision in the court. Okay, so we have this. And we want to know whether our jury is fair or whether it was chosen at random from the population. Okay, and that's because, for example, in California's law, it says blah 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 shall be selected at random from a source or sources inclusive of a representative cross-section of the population of the areas served by the court. The idea is we want the jury to reflect the community, right? We want the jury to kind of reflect the population of whatever group you're getting, of the court, the county that the court's in. The Sixth Amendment to the US Constitution says, the accused shall enjoy the right to a speedy public trial blah, 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 by an impartial jury of the state. Okay? So this is state law, constitutional law. We basically want people to be treated fairly in court. And so we want our juries to also be fair. Unfortunately, sometimes the fairness of our jury is cast into suspicion. In the case of Robert Swain versus Alabama, which happened in 1965, the court this man was tried in. So basically, Robert Swain was a black male, and he was convicted of a very serious crime, raping a white woman. Okay, so he was convicted of this serious crime. It turns out that in his case, 26% of residents in his county were black. Okay. However, in his jury panel, 8 out of 100 panelists were black. Okay. And then because the prosecution, so in the way court works is that the prosecution and the defense get some number of what's called a peremptory challenge, where they can say, okay, I don't want these members of the jury in my juror. I don't want these people in my jury panel because of some reason, right? So they have some limited number of those challenges, and you can use those challenges to just delete people from the jury panel because they think that they're biased or blah, blah, blah. They think they won't represent their opinion. Okay, so they both have some equal number of peremptory challenges, and all 8 of these black residents were struck from the jury by prosecution, so the final jury had no blacks. Okay, and this seems kind of suspicious. It was 1965, so it went to the Supreme Court because he appealed that, okay, this seems kind of suspicious. And the ruling by the Supreme Court was the overall percentage disparity has been small and reflects no studied attempt to include or exclude a specified number of black men. And unfortunately, Robert Swain got convicted. He got convicted of rape. Okay, and got sent to, I think he got the death sentence. So we want to know, so as statisticians, we really want to know, what is actually fair? Like this 26% going down to 8 out of 100, because this part right here is where this random selection was supposed to happen, right? Was this part actually fair? Like, is it possible to actually get only 8 out of 100 panelists when the original population was 26%? If it is pretty easy to get that, then we can say, okay, it's probably likely that it was selected at random. It's not hard to really say anything about it. However, if this thing right here is really unlikely, like never get 8 out of 100 because that's way too small, then we can say, okay, it seems like there's some problem in selecting the jury, right? It was unfair. So the question is our actual jury panel likely? Let's figure out why. Let's figure out what it is. Is anyone still taking attendance? Excellent. Close that. All right. So here I have just a table that contains the ethnicities of people in the Alabama County. So here I have people who are black and people who are not black. Basically, because we're looking at the black, we're looking specifically at the black proportion. Okay. In my county, there are 26 blacks eligible, 26% of people eligible. Here, of other ethnicities, 74%. Okay, so this is my distribution of eligible people to put in the panel. And in my actual panel, 8% of the panel were black as 8 out of 100, and the other 92% were other ethnicities. Okay, so I have that. So I want to figure out, so my big question is specifically, what is the probability of getting 8 out of 100 blacks in a panel? Right, so that's my big question. Because if that probability is really, really low, then I can say my jury panel was probably unfairly selected. If the probability is high, or even like not that low, if it's like, even if it's like 20%, I can say, okay, fine. It seems like, seems pretty okay. So I really want to know that probability. What I'm going to do is I'm going to start with these distributions. So start with distributions of the eligible panel and the actual panel. Okay, so I'm going to start with those. The second step is, so I can't actually compute that probability. So you can compute it, but it's pretty difficult to actually compute it. What I want to do is I want to simulate it and empirically determine what that probability is. So when I empirically determine what that probability is, I'm going to draw random panels from my population. Okay, so draw panels from my population. Population. Okay, draw panels at random. If I draw panels at random from my population, just like how I rolled my dice, or just like how I drew planes out of my 300 warplanes, I can then figure out, estimate that probability. See if my panel was likely. Okay, see if the actual panel is likely. So that's kind of my 3 high-level steps. This is what we want to do in order to figure out whether this jury was actually selected at random. Okay, so our question has changed a little bit. Before, we were trying to use a sample to estimate a number about the population. Now we're trying something a little bit different, which is take my sample, which was 8% black, 92% other ethnicities, and see whether it came from my population, which is 26% black. Okay, see if it was likely to get this panel, if I selected randomly from the population. Any questions about the setup? Okay, so, well, step 1 is done. I have my eligible distributions. And I can also take my table, Swain, and I want to bar H. Let's just show you the differences in the distributions here. So, okay, so my eligible, I had this much. And in my panel, I had this much. Okay, so just a visualization. All right. Let me first make a brief digression and talk about a way to measure the differences between distributions. Okay, so before we were looking at, say, the number of warplanes, right? To tell the difference between our estimate and the actual value. So let's say I took 20 warplanes, took the max of it, I got like 290, and I had 300 actual planes. To figure out that difference between my estimate and the actual value, all I have to do is subtract, right? All I have to do is do 300 minus 290. Okay, I was 10 off. That's an easy way to measure how far far off something is. If instead I had done the estimation and I had gotten 280, then I can say, oh, I was 20 off. So I was 10 off before. Another estimation might be 20 planes off. So I can say, oh, okay, like I can say, okay, the estimation with 10 off was better than my estimation with 20 off. So I get this natural ordering of how bad or good my estimations are. With distributions, it's a little bit trickier, right? Because I can't just do subtraction of 26% minus 8. I have other numbers here. And if I had other categories, those other categories need to get factored in as well. So the way that we like to measure differences between distributions is using something called a total variation distance. Okay, so if I just had numbers, the easiest thing to do is just to subtract and take the absolute value. with distributions, I can't exactly do that, but I can do something pretty close. So I have Swain. We call this total variation distance. So instead of just subtracting, I can take each column and subtract. So I take every column, subtract, and see if that gives me some measure of how different these two distributions are. Okay, so I have here Swain. And if I take this column eligible, column 1, and subtract it from Swain dot column 2, I get back, so here's my original table. Okay, I get 26 minus 8%, which is 0.18, 74% minus 92%, which is negative 0.18. Okay, so I have here differences. My first thought might be, okay, take my differences and sum them. So I do np.sum, and I get back 0. Well, this is like not exactly 0, but close enough to 0 because it's 10 to negative 17. So it's a rounding error. We say it's 0. Unfortunately, it's not super great because this panel is pretty different from my eligible population. So instead of taking the sum of just the numbers, I noticed that here my 18 and negative 18% cancel out. So I really want the absolute value of the differences before I take the sum. So I can just do sum. Okay. So now I say, OK, now I have this 36%, or 0.36. It's not exactly 36%, but it's like 0.36 difference, right? And what I can do is I notice that, again, this Swain dot column 1 is like 8. This is right here, 26 minus 8 is 18%. This right here is negative 18%. I'm kind of like doubling up my 18%. So I just divide this whole thing by 2 and get 0.18. So this is just the definition for what I call total variation distance. Okay, so I'm going to call this TVD. TVD. Okay. It's nothing that special. Okay, so there's some math here, but basically my point is the closer two distributions are to each other, the lower my TVD. Right? So if my two distributions are exactly the same, my TVD is very low. If my two distributions are very different, my TVD is very high. That's the only thing this TVD thing is doing. Okay, so I get a measure of how different things are, just like how I get a measure of how far away my estimate is from my actual, in the plain example, how far away my estimate is from the actual n, just by subtracting in that case. In this case, I need something a little bit more sophisticated to work with distributions. This is the measure of difference. Okay, so higher number, more different. Lower number, more similar. Okay, so that's the thing you should remember about the TVD. So I'm going to use that and use that to compare panels. So here's my measure of difference. What I'm going to do now is simulate. Okay. Well, first, I think I'm going to use this TVD a lot, so I'm going to define a function to do this calculation, so I don't have to do it every time. So total variation distance. And it takes in two distributions, which are just arrays. So I'm going to call this dist1, dist2. And basically, it's just this. Instead of using Swain dot column 1, I'll just use dist1. Column 2, dist2. Okay, which means that I can just calculate this. So I can just do this. Swain dot column 1, Swain dot column 2, stick that in there. And to return. Return. Okay, so same thing, just in function format, so I can reuse it later. Okay, so same thing. All right, now let me take some samples out of my population. So I'm going to sample panels. Right, so I have here Swain panels. My first thought might be, I used a sample method before. Why don't I just try a sample method now? So Swain.sample pen. And I get this. What happened? Why did I get this? Is this helpful or not? Talk with your neighbor for a minute. What is going on here?
One of these.
So why did this happen? Why did this result happen? What do I actually want? Okay, so this looks problematic. What do I actually want to get out of my sampling? Go ahead and talk. All right, so why is this problematic? This is problematic because I'm just picking rows out of my original table, right? So my original thought, if I scroll back up, is draw panels at random, right? Which means draw 100 people from population and then look at the proportions of blacks and people who are not black. So that's my original goal. When I take this swaying.sample, all I get is like other 74%, 92%, other 74%, 92%. It's not actually helpful for me because I'm not actually drawing panels for my population. I'm just taking rows from this table. So it's not, I can't actually use this for anything. So instead what I want to do is I want to say, OK, my population is 26% black, 74% other. I want to draw 100 people from those at random. What I want to do is instead of taking .sample, I have to do something a little bit more complicated, which is taking swing and grabbing out that first column, or grabbing out, so using select to grab out a table containing that first column. So here are my ethnicities, my possible ethnicities. Okay. And what I want to do is I can sample out of this ethnicities. So if I take ethnicities, and now I do .sample 10, I get back a sample of 10 people, right? So I have here black, 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 other, black, 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 black. Okay, so here's 10 people, my population. And the problem with this is that the chance that I get black and other is the same, right? Because the way this .sample works is I sample out black and I sample out other, but both black and other have equal probabilities. So here I have a panel, a quote unquote panel of 10 people, but it's going to be about half black and half other. I don't want it to be half black and half other. Instead, I want it to be as if I had taken it from my actual population, which was 26% black, 74% other. So in my actual panel, I should see, on average, less blacks and more people of other ethnicities, right? So I don't want to do just sample 10, although it is getting me closer. I want to instead do sample with some different weights. Okay, so I have my swaying table. I want to say sample according to these proportions. Don't sample 50-50. Sample 26% black, 74% other. Okay, so I'm going to take that column, eligible. And it turns out that this right here, I can use that in sample to say sample at these specific proportions. So here is my population distribution. Here it is. And when I do .sample, I can pass in an additional argument called weights. Weights equals popdist. And now you see I get a lot of others and not that many blacks because I'm sampling according to the population distribution, right? So on average, my sample will contain 26% blacks, 74% others. This is how I'm sampling. I'm drawing panels at random from the population. Yeah, question?
The rows and ethnicities, do they correspond with each index into the array that you create? So on distribution. So if you're to switch black and other.
That's right. So that's a great question, Ilian. So Ilian's asking, if I happen to switch these two, I've got these mixed up, then I would have sampled blacks at 74% and sampled other at 26%. That would have been flipped. The proportion would have been flipped as to what I wanted. That's right. So I have here a panel of 10, but I really want a panel of 100 people. So here's a panel of 100 people. And this is as if I went into my county, grabbed out 100 people at random, and now I have my panel of 100 people. On average, 26% of those people will be black. Okay, so here's my random simulation draws. Any questions about that? Okay, so now I have one panel. I can look at the proportion of blacks in my one panel. So here we go. Going to take go like that. And I can group by my ethnicity. I have 28 black, 72 others. And what I can do there is I can say, OK, group. And then what I want to do there is grab out this count column and divide by 100 so I can get the proportions. Okay, so I'm going to call this my sample panel equals that. Let me parentheses this so it's more easy to read. Sample panel. Here are my counts. Column count. Here are my counts. In this panel, I got 32 blacks, 68 others. So I run it again, 27 blacks, 73 others. Okay, so what I'm going to do now is add that, calculate proportions from that. So counts. Select 0 with column. Okay, so to my sample panel, and I just want to take that, divide by 100. So here are my counts, here are my proportions. 100. Okay, so here are my proportions of blacks and others. What I can do now is take my swing. I can just show you, I can just compare with you the proportions of blacks and others. So I can take that and add another column, random, and I can put in my proportions. Okay. And the thing here is not formatted correctly. I can just go back up here and copy that. So here we go. This is just a display. Oops. With column proportions. So with random, what's that? There we go. 1, 2, 3. Okay, so what I did there is I'm just taking a panel. I'm just showing you the differences between. Okay, so in my population, I have 26% blacks eligible. I have 8% in my actual panel. I have 23%. Okay, so I get this. Now what I want to do is I want to draw multiple panels. Okay, so I draw a bunch of panels and see whether this panel right here is likely to appear by random chance. Okay. So what I'm going to do is I'm going to do this. I have to do this a bunch of times, right? So I'm going to put that into a function so I can repeat it. I'll do def random jury panel. Oops. Okay. And I'm going to take this, put it in there. And I'm going to take that, put it in there, copy and paste, copy, paste, copy, paste. And I want to return this table. If I run this random jury panel, I get back another panel. I run it again. And it's not changing, unfortunately. That's because I forgot to do this. Okay, let's do that. Oops. Okay. So now I'm getting random panels. These are the panels that I'm getting. Okay, so 24%, 24%, 27%. Cool. So now I just need to do this a bunch of times and see whether my panel was likely or not. Okay. So what I'm going to do there, so what I'm going to do now is I'm going to take this simulation, I've run it a bunch of times. I'm going to take this random panel and take the TVD. So take the difference between the random panel and the eligible panel. What that gives me is a measure of difference, right? So these random panels, they're different from my eligible panel because they're drawn at random. I want to see whether those differences are likely. I want to see whether my actual panel's difference is likely. Okay, so what I'm going to do there is I want to repeat this process a bunch of times. So for loop, I'm going to call this repetitions. Let's say I want to do 1,000. For I in np.a range, repetitions. And I basically just want to call that. I'll call this my new sample. I want to find the total variation distance between my random and my eligible. That gives me a measure of how different random panels will be for my population. Okay, so I'm going to say keep track of my TVDs, array, and I want to add that TVD to my array. np.append TVDs with my total variation distance of the way total variation distance worked, I don't remember, is to do that. Takes in distribution 1, distribution 2. So I want to take in a new sample, column number 1, and the difference between my new sample column number 1 and column number 3. Column number 3. And now I can look at my TVDs. Take a look at what they are. Here we go. So I have a bunch of TVDs. So what this is saying is I took one random panel. That random panel was about 0.03 away from my population. Okay, so random panel drawn from my population was about 0.03 away from my actual expected results. I drew a second panel. That panel was about 0.04 away from my population. Okay, so what I want to do is I want to take those TVDs and put them on a histogram. Okay, so that's really long. Put that into a table. So results equals table with column. I'm going to call that TVD between population and a random sample. Okay, so that, make sure it's readable. I'm going to put in my TVDs, and here are my results. There we go. Okay, so we have a bunch of TVDs from a bunch of panels drawn at random from my population. So after that, histogram is pretty easy. I can see there that, OK, it looks like I drew a bunch of panels. Most of them were about 0.04 away, 0.06 away. I got a couple that were like 0.10, 0.10 away. So I want to look at my actual results. So let's look at my actual table. And if you recall, I believe I saved that TVD between the eligible and the panel in TVD. The actual TVD was 0.18. Okay, so think about what I've just done for a second. I've taken my population, taken the actual panel that was in my jury, and I said, OK, is this panel likely to occur by chance? Is this panel likely to occur if I drew at random from my actual original population? To figure that out, I actually took panels from my population. So take panels of 100, take panels of 100. And I looked at all the panels from my population and said, OK, I noticed that these panels are about this similar to my population. I can now take my original panel in the actual court case and say, was this panel likely to occur by random chance? So is it? I'll leave you with that for the weekend. See you next week.